expect something like this, don't we? The velocity will increase linear because the slope of a velocity time graph is your acceleration. If acceleration is constant, then it has to be a straight line. Yes? You're supposed to know, you're going to say, yeah, I figured that out when I wrote my lab up. Okay. It's the learning curve. How does this picture change if I suddenly quit pulling?
Eventually, it'll start going back.
In other words, it's going faster, 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 but as soon as I quit pulling, what happens? It's going to be constant. And how do I draw a constant velocity? As a flat line. So whatever velocity it has when I quit pulling is the velocity it keeps. Does that make sense? There actually is a bit of, Antoine, don't feel bad. There actually is a little bit of a rounding here because it has no sharp corners. So what happens is that I can't suddenly stop pulling. I have to open my hand and let go of the string. So during that moment, there's a gradual lessening of the force which flattens that corner out. So there, you were right. Your intuition's right. It's not a sharp corner, but it can't continue to speed up once I let go. It has to sort of curl around to be that flat, constant velocity at the end. Does that make sense to everybody? What's the acceleration here? It's the slope of this line. What's the acceleration here? It's the slope of this line. But what is the slope of this line? Zero. And that's how we know that there's no net force on this anymore. Right? So it has to be flat. Indicate on the graph when the pulling stop. All right. So they're going to give you pictures, and you're going to look for stuff like this. Hopefully that, check it out before Friday, so that if you have questions, we can get you some help before you go home for the weekend. All right. All right. I'm going to look at number 12. All right, so number 12 basically says, an elevator is pulled upward so that it moves with increasing upward speed. Stop. So something's pulling up on the elevator and its upward speed is increasing. What can you tell me about the forces acting on the elevator? If I were to draw a free body diagram of elevator, what are the forces? Assuming we have the simplest system possible, what do we know? We've got at least two forces, don't we?
Yeah.
And one of them would be the weight, and the other would be whatever provides the upward force. How big should I make it compared to the weight?
Bigger.
Bigger, all right? And that's all we need to know, is it just needs to be bigger. All right, I'll call this tension. Just because if it's a cable on top of the elevator, that's probably a good word for it. So the tension needs to be bigger than the weight. Does everybody see that okay? All right, so they say it's pulled upward and it moves at an increasing upward speed. The force exerted by the cable on the elevator is constant and greater than the downward gravitational force. We took care of that. When the elevator is moving up medium fast, all I mean is it's not going rocket ship fast. When it's going medium fast, the force exerted by the cable on the elevator changes abruptly to just exactly balance the downward force of weight. Not quit pulling like we did here. I still pull, but I pull with exactly the same force that the weight is. If I were to draw a velocity graph, would it look different from this? It's a nasty equal question, because it's a very different situation. Let's first do this. If I quit pulling, and here's the deal. If this was the situation, before I quit pulling, this would be what would be happening, right? I'd have a constant acceleration, it would be speeding up. If I did exactly like what I did there, and I cut the cable and quit pulling altogether, what would happen? Would it ever speed up past this point? No. In fact, what would happen is it would do this. As soon as you quit pulling, it's going to start slowing down and start falling. It won't necessarily fall. Okay. Does this indicate downward motion?
Yes. Wait.
No. I need to do this. It's not downward. It stops here. It's downward here. All of this is still upward because this is velocity, and all of these are positive velocities. Tricky, but think. If I suddenly quit pulling on the elevator, is it going to suddenly stop? No, it's just like if I throw a baseball up, the moment it leaves my hand, it doesn't start going down. It keeps going up till gravity can stop it. Are you with me? This is really important. When we look at this picture then, anything above the axis is a positive velocity, so all of these are still moving up. This is where the elevator stops, and this is where it starts to fall. Until the velocities go negative, you're not falling. So the trick is when you're looking at velocity graphs, don't think position. Because if this were a position graph, yes, that would be falling. But it's not a position. It's not saying where it is. It's not getting lower in the sky. It's getting slower, but still up. It doesn't stop till here because that's when velocity is 0. And stopping means velocity is 0. Okay? You've got a lot of stuff to think about tonight. All right? So this would be the picture that we would get if we actually quit pulling. If, on the other hand, I begin pulling with exactly the same force as the weight, what's the net force on the elevator? 0. Is that not what happened here? When I stopped pulling the string, I had a net force of 0. So the elevator would look exactly like this if I just pulled with the same force as the weight, because my force cancels the weight and doesn't allow it to slow down. It'll just keep going. Net force 0 means the velocity just stays wherever it is. Doesn't get faster, doesn't get slower. And if I'm pulling with the force equal to the weight, then whatever speed it was going, it keeps that speed, which is the picture we drew here the first time. Okay? All right. And then they just do the same thing where they're going to give you some pictures and you have to sort of figure out what they're trying to tell you. All right. Then the next one is pictures A, B, and C. Okay, so what they've done is they say these we've got 3 pictures of an object motion where what happens is these are basically time. We start here and as time goes by, these are the pictures of the velocity of the object. Talk to me about what's happening in each picture. In the first one on the left, what's happening? It's falling and increasing its speed as it falls. So we could say dropping something, that would be a pretty good representation of something that had dropped, right? What's happening in the second one? So it's like I've got a bucket, I'm lowering it into a well, and I'm not dropping the bucket into the well, I'm just lowering it at a constant speed down into the water. Probably none of you have ever actually seen a well, but that's okay. All right. And then what's happening in the last one? So give me a scenario where this could happen.
Repelling.
What's that?
Repelling.
Repelling? Do you climb rocks? Or rock climb or whatever? Or you just seen it?
Yeah.
I was going to say, if you've done it, I have not got the guts for it. I was just going to find out if you did. I've watched people rail and I go, the whole time I'm going, will this feel great? But yeah, yes, exactly. If I'm jumping down the cliff, what happens is I go down and I'm on the thing, then I want to come to a stop when I get to the ledge, I'm going to stand on it. So this shows me slowing down as I go down. All right? Very good. Okay, so let's kind of review. You get a lot of stuff today, but believe it or not, it's all tied together. Basically introduce Newton's 3 laws. The first law says, when the net force is 0, there's no acceleration. Hence, any velocity it has stays constant. Don't assume that it stopped. You can have a net force of 0 for objects in motion. All right? So that's important to understand. Then he said, okay, if there is a net force, then the object will have a change in velocity, which we call an acceleration. Anytime there's a net force that isn't 0, there will be an acceleration. And the acceleration will be in the direction of the net force. I didn't directly say this, well, a couple times I've alluded to it, but I want to reinforce. One of the beauties of talking about single dimension motion, like motion in one line, is that in 2-dimensional motion, we can treat the two axes completely independently. If I've got a vertical force, it can in no way ever influence horizontal motion. If I have a horizontal force, it cannot influence vertical. So we can analyze them separately. Nevertheless, even whether we do it separately or not, the first 2 laws I just said, they still hold. Net force 0, there's no acceleration, no change in velocity. Net force non-zero, there is an acceleration. All right, there is a change in velocity. And then the last one says, by the way, every force requires 2 objects, and those 2 objects exert equal and opposite forces on each other. Now, what we haven't learned yet, what this is setting me up for, is when I do the second law, and I say, okay, the net force causes an acceleration. It turns out that the acceleration that it causes is indirectly proportional to the mass. So if I have a net force acting on a big mass, it accelerates a little. If I have a big force acting on a tiny mass, it accelerates a lot. You with me? So if a guy's kicking a football, why does the football fly away? If the forces, according to that through law, says that we exert equal and opposite force on each other, so I kick the football kicks me, and those forces are equal and opposite, why does the football fly away? Because it has less mass. The forces are exactly the same. The force on me from the football and my force on the football's force on me, it's exactly the same force. But the football has a tiny mass, so it accelerates a lot. I have a big mass, so I don't accelerate very much at all. And if you don't believe that, try kicking a football that's full of cement. Right? Suddenly it doesn't do so much fly, and you do a little cry. So the thing is, it has to do with the relative masses. All right, so and we'll talk more about that. Then we just got the pictures that we take a look at. Get used to drawing free body diagrams. Here's the thing: when you go to put a force on something, if you can't think of two objects causing that force, don't draw. Until you can think of the second object, don't draw, because the biggest problem people have is they draw forces that can't exist because there's no other object to create that force. All right, guys? Yeah?
I have a kind of a question that I imagine was kind of a different thing associated.
All right.
How exactly would this sort of tie into a vacuum?
Actually, vacuums help us because we're continually ignoring air motion. And so in a vacuum, we actually do get a little better. We can get constant motion out of space because no air motion. Oh. You mean what's pushing the dirt in?
Yeah.
All right. What happens there is that we actually have a difference in pressure. The difference in pressure does cause pressure gradient, and yeah, we're not ready for gradient, but it causes a pressure gradient on the outside of the vacuum, which picks up small particles. But it's not as effective as people think. That's why vacuums have to have brushes to flip them so that they're airborne.
There's also clear that
So guys, you're excused if you'd like to go, and I'm going to go ahead and answer this question. Yeah. A lot of that it has to do with how close it is or how fast it is.